Okay, so do you want the wall off or what? Right. The introduction of artificial light into the nighttime environment represents the most drastic change to the nighttime. It masks natural light cues and it basically turns night into day. So I've heard orientation. While health impacts relatively little overlap between these two fields. And if these are having all these impacts on humans, they're likely in my research is trying to bridge this gap. In this study I'll tell you about today, I'll focus on as well as a measure of health, which is oxidative stress. So just a brief overview. Oxidative must exist in equilibrium with antioxidants. If the system is disrupted through either depleted antioxidants or increased reactive oxygen species production, so this could be cell damage, tissue injury, disease, among many other things. Since approximately 80% of all marsupials are nocturnal, they're likely to be highly impacted by well-established reproductive cycle, which is controlled by changing light levels. So it makes an ideal model for studying impacts of light at night on marsupials. So the tail is considered to be seasonally reproductive. That is, it breeds once a year. Unlike the red kangaroo, which you can see in the top up here, it's able to breed by 80% of females giving birth. But this is ultimately controlled by melatonin. So we know melatonin conveys information about time of day, but it's also able to convey information about the time of year. So in summer, we have this short duration of melatonin, but a higher amplitude. This is in contrast to winter, where there is a longer duration, but a lower amplitude of melatonin through the night. And this here is a typical melatonin profile of a tamal wallaby during summer. So you can see the peak in the dark phase, and it drops right down during the light phase. So this ultimately controls reproduction through we have the longest day of the year, the summer solstice. Following this daylight, so this increases amount of darkness, increases melatonin. It acts on the pituitary, it decreases prolactin, acts on the ovaries, and increases progesterone, results in this ultimate reactivation of the process. So in short, increased darkness increases melatonin, increases progesterone, and that results in reproductive activation. So my work's followed on from a field study conducted by my supervisor, which was done in Western Australia on Garden Island, where we have Australia's largest naval base. Now on the island, there's two populations of tamal wallabies. There's one in the south of the island, which is around the naval base. So these animals experience high levels of at night. In contrast, so they put some collars on animals and monitored their experience light levels. So in the bush animals, you can see that they have this cycle that followed full moon. On the bottom, you can see the base animals, which experience really high levels of light at night throughout the entire study period. And if you notice on the axes, there's a whole magnitude of difference here. So if we look at it together, even though bush animals had fluctuating levels of light, the levels they experienced didn't even come close to that experienced by base animals. Now this ultimately resulted in suppressed melatonin. So in our bush animals, we have high levels of melatonin, which is consistent with normal levels of thermal voltage during summer. In contrast, base animals had significant melatonin suppression. This ultimately resulted in a 4-week delay in reproduction in these animals. So in our bush population, they had that in late January. In contrast, we can birth take base animals 10 weeks after. So this is a 4-week delay in reproduction in these animals. This is extremely significant for a species that is undergoing late lactation when there's potentially not enough resources. However, all these impacts were only observed under traditional high-pressure sodium light. With the introduction of white LEDs, we're likely to see a significant increase in these impacts. So we've all seen the spectrum of these white LEDs that have that large peak in the short peak wavelength region. Now these are the wavelengths known to have the greatest suppressive effect on melatonin. So for my study, I worked with an industry partner to develop LED lights that cut out these short wavelengths. So I was testing them on the tunnel walls, looking at I used to capture the population of tunnel walls, which we have at university, and I had 3 things. I had dark control, our short white LEDs, and our long wavelength amber LEDs. So we have lights control. I used it before or after control impact design, so I took measures at baseline at week 0, trapping animals in these soft-sided traps, and then following 10 weeks of light at night. I used micro light loggers to measure the spectroradiometer and a handheld spectrometer to measure the spectral composition of our light. Then later assays put up the peroxidation and antioxidants. So what did this look like? So these are the results of our lights. You can see our white lights on the left, which have that typical peak in the short blue wavelength region. The peak of these lights occurred at 448 nanometers. This is in contrast to our long wavelength amber LEDs. However, if we look at our lights together, you can see our white LEDs in green and our long wavelength amber in pink. You can see that it wasn't just the peak of these lights that shifted, but the entire spectrum was shifted towards long wavelengths. And we were able to completely cut out. What did this do to the animals? First, we'll look at melatonin production. So we've got our mean melatonin concentration and our 3 treatments. So when we look at our control animals, we can see that there was no change in melatonin across that 10-week period. This was reflected in animals under our long wavelength amber LEDs. They experienced no suppression of melatonin across this 10-week period. This is in contrast to animals under white LEDs, which showed significant melatonin suppression across that 10-week period. When we look at lipid peroxidation, so our mean lipid peroxidation concentrations in the same 3 treatments, we can see that levels declined under all treatments. However, this decline was only significant under our control. If we look at week 10 alone, there was still a small trend for slightly higher levels under our white LEDs. But since we don't have baseline measures of what is considered a normal level in these species, we're unable to determine if the levels we measured at the start and end of the study are considered high. When we pair this with our antioxidant concentrations, we can see that levels decline significantly under all treatments. And this can often be misinterpreted as an unhealthy state, whereas this might actually reflect our results together. We found evidence of melatonin expression under our short LEDs, but not under our long wavelength amber LEDs. We didn't really find any change in the peroxidation, but as I said, this is just an indicator for oxidative stress, and it might not necessarily be the most ideal measure. We were conducting an ecological study where we were using minimally invasive measures. There was actually another study done on hamsters, which took several measures of oxidative status. And they measured protein damage and also measured lipid peroxidation. They found minimal change in lipid peroxidation, while they found levels of protein damage occurring in these animals. So this also suggests that we may have missed some underlying health impact. And again, for our antioxidants, there was no observable treatment effect. These declined under all treatments, so this could be seasonal changes. However, the mollies we looked at only possessed a wide range of species with different visual capabilities. So a diachromatic species has two kinds of colour vision. They have a short and a middle wavelength bone. While for a human, a trichromatic human. So we can see our circadian sensitivity in the dashed line, which is focused around those short wavelengths. On the visual sensitivity, ranges from short to long wavelengths. But what does this mean in the context of our lives? When we our long wavelength amber lights completely fall outside. Results for at the moment, and I'll hopefully be presenting to you next time, is using the fat tail dunner as a marsupial model. This is a small nocturnal marsupial. It possesses trichromatic colour vision, so this enables us to look at any behavioural impacts of our long wavelength light. It is also a seasonal breeder cued by changing the light cycle for the winter of short days, long nights, and of long days. So just briefly, in this species I've used surveillance footage, we've got 3 treatments, so a dark control, our white LEDs, and our long wavelength amber LEDs. So I've collected 24 hours. I'm looking at the onset of reproduction of this species. So in females, we can identify the onset by collecting urine. So I collected urine samples from females and looked for the presence of these epithelial cells. So females shed these all the time, but when she's in estrus, these cells appear in high numbers and they start to clump together. I was also looking for any upregulation of reproductive output in males by collecting urine samples and looking for the presence of sperm in urine. And finally, a better measure we could be using. So I'm doing this by looking at daily food consumption in these species. There's been similar rodent studies which have identified obesity following light at night. I was also able to take body weight and body composition measures. So body composition was done. Finally, I'm looking at simulation. So by collecting food and fecal samples before and after exposure to lighting, I'll be using bomb calorimetry to determine the calorific value of these samples. They'll be able to determine the amount of energy assimilated by the animals. Finally, I'd just like to thank everyone involved, volunteers, supervisors and all our funding bodies, and I'd like to welcome any questions.
Got any questions?
This might be my understanding question. Moon light is so much thinner than sunlight. Does it have any personal effect on the website?
The answer to that is yes, it does. It's a simple.
I find this kind of work really fascinating. One of the questions I had in regard to the wallabies, because you have the bush wallabies and you have more wet environment. If you look at what was the threshold where it swapped from one.
So there's sort of 2 isolated populations.
Yeah.
one more, yeah?
I think that was really great and really interesting research. Did you look at the light intensity?
Yes,
Because you said you
I
did
did.
it, I think.
Yes, so that's all in the paper, but I'm going to show you graphs later. So between our two models, they were the same when we measured. So I measured light intensity directly under the lights and the distance away from the lights, and we ensured that both of those were significantly higher than the starting levels, although it did disperse some distance. So there is a
You can see that's what made that intensity made a difference.
Yeah, so the animals were free ranging. So in terms of behaviour, previously prior to starting the study, I read another paper which suggested that terminal wallabies associate light with higher safety. And this didn't seem to make sense at first for nocturnal species until I actually observed our animals on white lights hanging out under the lights. So they were sort of almost forcibly exposing themselves, but that's been interpreted as they are able to see their predators better. So yes, their nocturnal predators might have better vision with them, but they also detect their predators.
Thank you very much.